Hi everyone. So far in chapter 8 we've learned the derivative of e to the x and the derivative of natural log x. And now what we're going to do is real quickly talk about what if it's a different base. So let's start off by just reminding ourselves. We learned that the derivative of e to the x is e to the x. It's one of the easiest derivatives to use. So now let's take a look at an exponential with a different base. And I'm going to call it a. A could be any number. You might have 2 to the x or 10 to the x or 7.3 to the x. You know, the base can be any positive number. And here's how it works. You have the derivative of a to the x. It's kind of a two-part answer. The first part works just like e to the x. So the derivative of a to the x is a to the x. But it has this extra constant on it right here. You multiply it by the natural log of the base. Now there's no x in there, that's not a variable, that's why I said it's a constant, and it's basically just something you multiply at the end. So here's our summary. This is how to take the derivative of any exponential function. Number one, the derivative of e to the x is e to the x. That's an easy one. For any other base, you do the same thing. The derivative of a to the x is a to the x, but you include a constant term, natural log of whatever that base was, multiplied to your answer. Then, once you know how to do that, we're going to apply all the problems we've done all year and what we just reviewed with e to the x and with natural log x, things like chain rule, product rule, etc. So here's our first example. We're going to find f prime here, and we have 10 to the x squared. So what I'm going to do this just like it was e to the x squared, meaning this is going to be a chain rule question, but then I'm going to have an extra term on the end. It's going to end up being natural log of 10 since my base is 10. So for any exponential, the first part of your answer is the exponential function itself. So I'm going to say 10 to the x squared. Then I'm going to multiply by the chain rule. I say, well, it wasn't 10 to the x, it was 10 to something else. So I have to multiply by the derivative of the exponent, which would be 2x. Then we have one more step here. If that was e to the x squared, we'd be done. But since it's a different base, we have an extra constant term. We have to multiply by the natural log of 10. So all three of these things together give you your answer. This one right here is basically the original function. This one right here is the chain rule. And this one right here is the extra constant term that happens because it was a different base. It wasn't e to the x squared, it was 10 to the x squared. So you got to remember each part. There's a lot to remember here. But basically, if you just kind of push all that together, those three things in any order are your final answer. So I might say for my final answer, I might say it equals 2x natural log 10 times 10 to the x squared. And that's like my preferred order, but remember, as long as you have the three correct pieces pushed together, you don't have to have one first, second, and third. It's multiplication, it can go in any order. So that's how that works. The first two parts of that work just like e to the x with chain rule. But then you say to yourself, oh yeah, that wasn't an e to the x, that was a different base, so I got to remember my extra constant term of natural log whatever the base is. All right, here's another example, and this one is going to combine it with product rule. So you can see by looking at the question, my function is 3 to the 2x minus 5 times natural log of x to the 4th. So let's go ahead and do this as a product rule. So when I go to find f prime of x, this right here is my first function, 3 to the 2x minus 5. And this one right here is my second function, natural log of x to the 4th. Let's do the derivative of the first function. So that would be the original function, 3 to the 2x minus 5. Chain rule, I have to multiply by the derivative of the exponent, which is actually just 2. Extra constant, because it's not an e to the x, it's a 3 to the x. And that would be natural log of 3. So that one part right there is exactly what we did in the last example. That's just taking the derivative of an exponential function with a base other than e and using chain rule on it. Okay, so it's derivative of the first times the second, that would be natural log of x to the fourth, plus derivative of the second. So we're going to go back to what we learned in the last section about our natural log derivative. The natural log derivative is the one we sometimes call the reciprocal derivative. So it's going to start with 1 over x to the fourth, but then you multiply by the derivative of x to the fourth, that would be your chain rule. And that's going to be power rule. The derivative of x to the fourth, you multiply by 4, lower the exponent by 1, you get 4x cubed. And then we have one last step. We have derivative of the first times second plus derivative of the second times first, and the first function was 3 to the 2x minus 5. So we have to stay organized there. There was a lot of work going on in there. When I go to clean up my answer, let's see what we get here. The first one, it basically just probably kind of push it all together. You get 2 natural log of 3 times natural log of x to the fourth times 3 to the 2x minus 5 plus, now on the second one, this x cubed will cancel with 3 of those on the bottom, and you're just going to have 1 over x. So I'll have 1 over x times 3 to the 2x minus 5. Now at this point, or actually you could have noticed this on the very first step, you have a common term, that 3 to the 2x minus 5 here or here. You might want to factor that out. And then what you get is 2 natural log of 3 times natural log of x to the fourth plus 1 over x. I'm going to leave that. We could maybe clean that up a little bit more. You could, take care of that 1 over x, but I'm just going to leave it at this point. You guys get the idea, though. That was product rule, which you know how to do. We've done that. But it's applied to, or not applied to, it has a exponential derivative within it. Okay, so let's switch gears and let's do the derivative of a log with a different base. So I'm going to do the same thing. I'm going to use a to stand for any base. Here's the derivative. You have the natural log of, you have the log base a of x. And what you notice is it, kind of like what we just did with e to the x, it has the derivative of natural log x in it. It's still going to be a 1 over x thing, a reciprocal thing. But it has that extra constant again, just like we did with a to the x. Now this time, the extra constant, the natural log of a, goes in the denominator with the x. So a good way to think of this derivative in words is to think, okay, any log, the derivative of any log is a reciprocal. It's that 1 over x concept. If it's a natural log, it's just 1 over x, period. If it's any other log, you do the 1 over x part, but with that x in the denominator, you get that extra constant, that natural log of whatever the base was. Same constant also. It's natural log of a for both of our derivatives today. So here's our quick summary again, and this is kind of what I just said in words. The derivative of natural log x is just 1 over x. The derivative of any log, any other log, you still get that 1 over x, but you have the extra constant here, that natural log a that gets multiplied into the denominator with the x. So let's see how this one works out. We're going to do f prime here, and my function is not natural, it's log base 6 of x cubed plus 3x. So when I go to find my derivative here, f prime, I say, well, first of all, let's kind of pretend like this is a natural log, because we start the question the same way. And what that means is you're going to start off with the reciprocal of whatever is in that log. So this thing right here, whatever I'm taking the log of, you start with the reciprocal of that. So I'm going to start with 1 over x cubed plus 3x. Then I do the chain rule. I say I'm going to multiply that by the derivative of x cubed plus 3x. Now the derivative of x cubed, power rule, would be 3x squared. The derivative of 3x would be 3. Now we have one extra step here. This is the only difference between natural log and log base 6 or any other. I need to, in the denominator here, with that x cubed plus 3x, I just need to sneak in a natural log of 6. And that's it. That one extra constant term is the only difference between a natural log derivative and any other log derivative. And we just did the same thing with e to the x and a to the x. So to finish up this question, I would really just take this and multiply it up top there. So for my final answer here for f prime, I would say 3x squared plus 3 over x cubed plus 3x times natural log of 6. And again, one more time, that natural log of 6 right there, this thing right here, is the only difference between this log question and a natural log question with the exact same thing. If I ask you guys to find the derivative of natural log of x cubed plus 3x, you get the exact same answer, but without the natural log 6 in the denominator. And that brings us to our summary today. Here are your 4 derivatives for any log and any exponential function. And I said up top, I said this is the shortcut here is to memorize these. You know, when it comes down to it, when you're doing derivatives for logs and exponentials, the shortcut is just know them. And what it comes down to also is that these two right here are by far the most common. If you guys take AP Calculus next year, when you take that AP test, of all the questions about logs and exponentials, probably 95% of them will be either e to the x or natural log of x. And maybe 5% of those questions, maybe 1 or 2 questions on the entire AP test will be the other two. So make sure you really, really know how to do the e to the x and natural log x ones. The other ones, it's good to know, but you're not going to see them nearly as often. But the good news is it's basically the same thing, except for that extra constant. You have an extra natural log a here and here, but other than what I circled in green, it's almost the exact same problem twice in a row.